Hi, Keys Precalculus. We are going to go over section 2.2 here. We began it in class today, and we're going to finish it here on the video so you can do your homework more easily this weekend. We talked about what the graph of a polynomial function would look like. We reviewed that if the power of the function or the degree of the function is an even degree, it's going to behave, its end values or the end behaviors of our graph are going to be like a parabola. They're either going to open up or they're going to open down over time when you zoom out. And we said if the power of the function or the degree of the function is odd, then it's going to behave like a line. It's either going to rise as you read from left to right or fall as you read from left to right. But in both of those cases, you can have some local extrema. That means in the middle there, you can have some maximum and minimum values. But overall, the end behavior, the graph is either going to open up or down if the power is even, or open or rise or fall if the power is odd. And we also talked about if you've got the parent graph, the higher the power, then the flatter it's going to be at that turning point, either like the base or the turning point of the odd powered function. You can see examples of this on the bottom of page 100, so you should go ahead and look in your book at that. Then we also talked about how to find the leading term of a polynomial. And don't forget that when you look at a polynomial, the leading term is not necessarily the first one. It's the term that has the highest power, or the variable with the highest degree. And in this case, by our definition, it's going to be the n term. In other words, if the degree is n, then a sub n means just the coefficient that goes with that degree. N minus 1 is going to be less than that, and so the coefficient a n minus 1 goes with the x to the n minus 1. All the way down to the power of 1, that a sub 1 just means the coefficient that goes with the variable with the power of 1, and then a sub 0 is the constant. But if see what I circled over here in blue? This, because n is the highest power here, this is the leading term, and the coefficient of the leading term is called the leading coefficient. And what does the leading coefficient do to the graph? Think about it for a minute. See if you can answer it. Yes, the leading coefficient is going to determine whether a graph rises or falls if the power is odd, or if it opens up or down if the power is even. So that leads us to what we call the leading coefficient test. So if we take a polynomial here, for the polynomial functions, f of x equals some polynomial where your leading coefficient is not 0, then it says when n is odd, when your power is odd, we know that the graph is either going to rise or fall in its end behaviors over time. But if the leading coefficient is positive, it's going to have a positive slope, and so the graph is going to rise when you zoom out over time, just like a line would be rising as you read from left to right. So the way that you write this or state this is, as x approaches negative infinity, as x goes that way, right here, as x approaches negative infinity, hold on, I'm trying to get my pen, it's not working. There we go. As x approaches negative infinity, f of x, or the function, is also going to approach negative infinity. So as x is going this way, y is going down, right? And then over here, as x is approaching positive infinity, as x is getting bigger and bigger and bigger, y in this case is also approaching positive infinity. Or f of x, the function, is also approaching positive infinity. So as x goes to negative infinity and as x goes to positive infinity, the functions are going in different directions. If a is positive, as x goes to negative infinity, the function is going to negative infinity. And as x goes to positive infinity, the function is going to positive infinity. And you can see I denoted that by x with an arrow to infinity, f of x with an arrow to infinity. That's how you write it down. That's how you state it in written form. Now let's talk about what happens when your power is odd and your leading coefficient is less than 0, or it's negative. Just like a line, when your slope is negative, as you read from left to right, the graph is going to fall over time. It's going to go decline or have a negative slope over time, right? Same thing with any odd-powered polynomial. It doesn't matter what the local extrema, what the local maxima or minima are. Over time, the end behaviors of the graph are going to behave as a line is, as you read from left to right, is going to be falling. So in other words, as x approaches negative infinity, y will be approaching positive infinity right here. So I'm going to write the positive infinity right here. And as x approaches positive infinity, y is going to be approaching negative infinity on the right side. So I'll just write a negative infinity here. So that's how the end behaviors of not odd functions, but functions with odd powers behave. When the leading coefficient is positive, it will rise over time. When the leading coefficient is negative, it will fall over time. But what if the power is even? If the power is even, that means the highest power is an even number, and the leading coefficient is positive. Well, first of all, if the power is even, it's going to behave, the end behaviors are going to behave like a parabola. It's either going to open up or open down. But just as a parabola, if the leading coefficient is positive, then the parabola is going to open up. Same thing if it's to the fourth power, to the sixth power, to the eighth power. If your polynomial is an even-powered polynomial, and the leading coefficient is positive, it's going to open up over time no matter what happens here in the middle. So in other words, as x approaches negative infinity, f of x is going to approach positive infinity. And as x approaches positive infinity, f of x is also going to approach positive infinity. So again, x approaches negative infinity, y is approaching positive infinity. As x approaches a positive infinity, y is also approaching positive infinity. That's how it works when your power is even and your leading coefficient is positive. Now, when your leading coefficient is even and your power is even and your leading coefficient is negative, it's going to go the opposite direction. It's going to open down. In other words, as x approaches negative infinity, y is also going to approach negative infinity. And as x approaches positive infinity, y is going to approach negative infinity. So I will write those answers, or those symbols there, here at the bottom. Okay, this is all on page 101 of your book. I know you did talk about it in Algebra 2, and so this is a review. But you can look at this as many times as you need to understand it fully and make it something that you don't really have to think about, you just know. Now, something I want you to understand or think about also is that when I drew these, I drew little dotted lines here in the middle because I wasn't giving you an exact graph. I was just giving you a representation of what an even-powered polynomial would look like if it was graphed. It could have several different relative maxima or minima here in the middle. It could have none, or just one if it's even, like the orange one. Or if it's odd, it could have several, or it could just be smooth and just be continually rising the whole time, like the graph on the bottom of page 100, or even in the 10 box on page 100 for you. But what you need to keep in mind here is that when a polynomial crosses the x-axis, it's said at the places where it's crossing, those are called zeros. We talked about those in class, and we'll talk about this a little bit more later. But those places where it crosses the x-axis are called zeros. And a polynomial f of degree n can have at most n real zeros. It doesn't have to have them, but it can have at that many. So if you've got a power of 2, then you can have at most 2 real zeros. If you've got a power of 5, you can have at most 5 real zeros. It will either cross, the graph will either cross or touch the x-axis n times. Like here, I drew a picture of it crossing the x-axis But I could also draw a picture of a polynomial graph touching the x-axis, just in one place right here, right? And then going off and doing its own thing. So, if a polynomial has a degree of 4, then it's either going to cross or touch the x-axis at most 4 times. It could touch it once, it could cross it twice, it could cross and touch 3 times, or it could touch it 4 times or cross it 4 times. Or it could do like this pink one and not cross it at all. It doesn't have to have that many. That's just as many as it can have. But if it has an odd power, the polynomial it's going to have to cross it at least once, because it's going to rise or fall over time. So it may cross it 3 times, cross or touch it, 5 times, whatever, or just once, but it absolutely has to cross it once. But once again, if you've got a power of 5, that's your highest power in your polynomial, you're not going to have 6 zeros. You're only going to have 5, 4, 3, 2, or 1. If you have a power of 6, you're not going to have 7 or 8 zeros. You're going to have either 6, 5, 4, 3, 2, 1, or no zeros. And we will talk more about this in another section, but I just want you to keep that in mind as you're studying these graphs, that they can, if you've got an odd power, it's going to cross it at least once, but no more than n times. And if it's got an even power, it's going to cross it no more than that n times, or it will not cross it at all. In addition, the graph of a polynomial is going to have at most, right here, n minus 1, oh, made a little heart, how cute, n minus 1 relative extrema. In other words, it's going to have either n minus 1 maxima or n minus 1 minima, or a combination of the two. For example, if you're given the polynomial x squared plus 1, f of x equals x squared plus 1, you know this is a parabola with the a vertex at 0, 1, and it's going to open up like this. So you know that this is a parabola. What is the power of this polynomial? The power is 2, so n is equal to 2. So you can have it cross the x-axis at most 2 times, but it doesn't cross it at all. And you can have at most 2 minus 1, or 1 maxima or minimum point. In this case, it's a minimum point. Every parabola is going to have a change in direction. So it's either going to have a maximum or minimum point, and there's only going to be one of them, and one is the power 2 minus 1. Another function up here, f of x equals x to the third minus x squared minus 2x. What's that going to look like? Well, I can see that my power is 3. That's an odd number, so it's either going to rise or fall. My leading coefficient is positive 1 here. It's understood because I don't see it. Therefore, let me erase that little line I drew so it doesn't look like a negative. Therefore, I know that it's going to rise over time. It's not going to open up or open down because it's odd powered. And it can cross the x-axis up to 3 times. And then it can also have up to 3 minus 1, up to 2 relative extrema, 2 maxima or minima. Now, this orange graph is a rough sketch of what that one is. It's not exact, but it's close. We're going to do a problem like this problem in a few minutes, but to graph it. But right now, we can see that it crosses the x-axis 3 times. And if you were to graph this on your graphing calculator or Desmos, you would see that it only crosses 3 times. And it has a relative maximum and a relative minimum. A maximum and a minimum point right there and right there. Only 2 of them. It can't have more than that. It doesn't have to have 2. It could have been continuous, but it does have 2. And it can only have as many as 2. Because n is 3, and 3 minus 1 is 2. Or I should say n is 3 in the case of this orange polynomial. Sorry, I'm having some technical difficulties right now. Okay, so what I'd like you to do is look on page 102. I want you to pause the video, look on page 102, and I want you to work through example 2 on your own. I want you to use the leading coefficient test to describe the right and left-hand behavior, the end behaviors of the graphs of each polynomial functions a, b, and c. Don't look at the answers yet. See if you can figure it out. Tell yourself how many times it could cross the x-axis and how many maxima or minima it could have. And then look at their solutions, check your work, and once you're done, come back here. But in fact, while you're doing it, you should write those things down to turn in with your notes when so I can check them. Okay? I hope that example was pretty easy for you. Now we're going to move on to talking about the zeros of a polynomial. Now, when we were in class today, we talked about what the zero of a polynomial is, or the zero of the function is. A zero of the function is where the graph of that function crosses the x-axis, like here, or here, or here. I'm having a hard time with my pen seeing the computer screen is pretty far away from me, so it's hard to see and the ink is small, so it's hard to see where to land. So anyway, I apologize about that. But it's the zero of a polynomial function, or the solution of a polynomial equation, is where that graph is going to cross the x-axis. That means it's the x value that makes the entire thing zero, that generates a zero for the y value, or generates a zero for the function. So if f is a polynomial function and a is a real number, any real number, the following statements are equivalent to each other. X equals a is a zero of the function is the same thing as saying x equals a is a solution of the polynomial equation f of x equals 0. In other words, a zero of the function is a value that makes the entire function end up equaling 0. And on a graph of that function, it is where that graph crosses the x-axis, because every y value on the x-axis is 0. In addition, x minus a is a factor of the polynomial f of x. What does that mean? Well, I just made up this problem here to show you what that means. If a is a 0, then x minus a is a factor. So let's say I have this polynomial f of x equals x minus 1 times x plus 1. And I want to know what the zeros are. Well, I would say that where the zeros are where it crosses the x-axis, where y is 0, or the whole function is 0. So I would say 0 equals x minus 1 times x plus 1, and I would solve for x. And that means that one of these factors has got to be 0. So either x minus 1 equals 0, or x plus 1 equals 0. So x minus 1 equals 0, that would be x equals 1, or x equals negative 1. So that means it's going to cross the x-axis at 1 and negative 1. Our graph is going to cross at negative 1 and at positive 1. And I know this is a parabola with leading coefficient is positive, so it's going to open up. So it's going to look something like that, right? So if my a are zeros of the function, then x minus a's are factors of that polynomial. And the points a0 and the second a0 and the third a0, whatever, are x-intercepts of the graph. So you need to understand this terminology as well. That's why we went over it. It is on page 103 of your book. Now what we're going to do is we're going to practice finding the zeros of a function, both algebraically and with our graph or graphing calculator or Desmos. This is example 3 on page 103 of your book, but I'd rather you follow along here. I also had written this up here in orange earlier. But the instructions say find all the real zeros of f of x equals x to the third minus x squared minus 2x. So the first thing we're going to do is we're going to see if we can find these zeros algebraically. This means that I'm going to set my function equal to 0, and I'm going to find what x values make this function 0. First thing I do is I look at all three of those terms, and they have a common factor of x. So I'm going to factor out an x, and I'm left with x squared minus x minus 2. So I've got two factors. I can say x equals 0 and x squared minus x minus 2 equals 0, but I could factor this even further to make it a little simpler for myself. So what two numbers can I multiply to get my constant, but add to get my middle term. In other words, what two numbers can I multiply to get a negative 2, but add to get a negative 1? Well, obviously, it's going to have to be a 2 and a 1, but which one's negative? So I've got x with a 2 here, and x with a 1 here. One of them has to be negative, one of them has to be positive. Since my middle term is negative, that means the larger number is going to need to be negative, or the larger absolute value is going to need to be negative, so my 1 is going to be positive, and my 2 here is going to be negative. So here are the three factors of x to the third minus x squared minus 2x. It's x, x minus 2, and x plus 1. One or all of those factors have to equal 0 in order for the whole function to be 0. So I can say x equals 0, or x minus 2 equals 0, or x plus 1 equals 0. Well, this one's already a 0, so there's one of my zeros. X minus 2 equals 0 leads me to x equals positive 2. There's another 0. And x plus 1 equals 0 leads me to x equals negative 1. So I can see that it's going to cross the x-axis at x equals negative 1 right here, at 0 right here, and at 2 right here. So now that I have my zeros, what is the rest of my graph going to do? Because this is a function and it's a polynomial function, so it's going to be continuous. So what do I have to do? Well, I look at my leading term, which is x to the third. Its coefficient is 1, so my leading coefficient is positive 1. So I know that this graph over time is going to rise. But it's going to also have some business in the middle. It's going to have some relative maxima and minima. Now, because the power is 3, it can have up to 3 zeros, which it does. And how many relative extrema can it have? It can have 3 minus 1, which is 2. So we can change directions twice. And if you think about it, it's going to change directions between the dots. So between the negative 1 and 0, it's going to switch directions. And between the 0 and positive 2, it's going to switch directions. In other words, it's going to have a maximum or minimum between the first two and a maximum or minimum between the second two. But we know that because the graph is rising over its in behaviors, because the graph is going to be rising, it's going to be approaching from negative, as x goes approaching negative infinity, y is going to be approaching negative infinity. So before this one, it's going to be rising. And it's going to change here somewhere, and then it's going to fall, and then it's going to rise again. And that is really what I care about when you're graphing. That you get this, you get the zeros, and you get the correct direction, and you see that it's got some rising and falling. But what you could also do is plug this into Desmos or your graphing calculator and trace it to see approximately where the relative maximum and the relative minimum is, and you can get those values more closely, or you can draw a more accurate graph. I do want you drawing these graphs on graph paper, but they don't have to be exact as long as you've got the right zeros and the right direction and the right number of relative maxima and minima. Now let's check our answers. Let's go back, and if we plug in this 0 into this original equation, 0 to the third minus 0 squared minus 2 times 0 is 0. So yes, 0 is the 0 of the function. What about 2? If I plug in 2 to this equation, 2 to the third is 8, minus 2 squared is 4, so 8 minus 4 is 4, and then minus 2 times 2, which is also minus 4, so 4 minus 4 is 0, so yes, 2 works, and then does negative 1 work? Well, negative 1 to the third power is negative 1, minus negative 1 squared is 1, so negative 1 minus 1 is negative 4, and then negative 1 times, no, I said that wrong. Negative 1 minus 1 is negative 2. And then negative 1 times negative 2 is positive 2. So negative 2 plus positive 2 is 0. So yes, all three of these answers do work. Okay, let's do another example. Let's look at example 4 on the bottom of page 103. It says, find all the real zeros and relative extrema of f of x equals negative 2x to the fourth plus 2x squared. So the first thing I'm going to do is I'm going to set my whole function equal to 0, and then I'm going to factor and solve for x. So I know I can factor out a 2, and I could do -2. It really doesn't matter. But I'm going to factor out a -2 in this case. I'm going to factor out -2 and then x squared, because that's the smallest power. So I'm left with x squared here minus 1. Because if I were to distribute this back through, -2x squared times x squared gives me -2x to the 4th, and -2x squared times -1 gives me positive 2x squared. Y'all see that? And all of this is equal to 0. Now, I can do one more factor. I can factor out that quadratic. I need to factor, so I have this quadratic, -2x squared, and then I can factor this. This is a difference of 2 squares, so that factors into x plus 1 times x minus 1. So now I have my 3 factors. I actually have 4 factors because this is x times x, but we're going to leave it as x squared right now, because I can just set each one of these 3 factors that I have equal to 0 to solve. So -2x squared equals 0, x plus 1 equals 0, and x minus 1 equals 0. So if I solve for each of these, I can solve this. This is easy. It's just 0. This is x equals -1, and this equals x equals positive 1. So I know that my graph is going to cross the x-axis at 0, at -1, and at positive 1. I also know that this is an even-powered function. So that means that it's either going to open up or open down. But my leading coefficient is -2, so that means it's going to open down. So in other words, it's going to behave like a parabola. But I can have some relative maximum or minimum points in the middle here. It crosses the x-axis 3 times. So remember, it can cross up to 4 times. It can cross or touch up to 4 times or none. And it can have up to 4 minus 1, so 3 relative minimum or maximum points. One way I can figure this is I could do an XY chart right here. And I could pick numbers to the right and left of my zeros. Like I could pick a -2 for x. I could pick between -1 and 0 is like a -1/2. I could pick a 1/2 because that's between 0 and positive 1. And then I could also pick a 2 because that's to the right of positive 1. And if I plug these values in to my original equation, -2x to the 4th plus 2x squared, I can find what my y values are and get a rough estimate. I could do that algebraically, or I could plug this in on my calculator and get a rough estimate of what it is. Now I went ahead and solved for my XY chart. You could pause the video and do it yourself, check my answers. So I know that if my x is going to be -2, my y is going to be somewhere down here, -24. So it's going to be rising very steeply from this to this point. And then it's going to go up to a half, and 1/2 is going to be about 3/8. So it's going to be somewhere here in the middle. And then it's going to go back down. It's going to touch at 0. And it's going to come back up to 3/8 again, and then it's going to go back down. So this is what my graph is going to look like. And if we zoom in, let's see if I can do that. If we zoom in, I can see I have a relative maximum here, a relative minimum here, and a relative maximum here. So I have 3 local extrema, and my graph does look like its end values look like a parabola. It opens down. Now, it's got a power of 4, so it can have up to 4 zeros, and actually it does. But one of them is a repeating 0. Sometimes you have answers that are not real, but in this case, all of our answers are real, and there are 4 of them, but one of them is a repeating answer. And what do I mean by that? I mean this x squared here is really x times x, right? So think of it as being -2x times x plus 1 times x minus 1. Those are the factors of this polynomial. And if negative 2x equals 0, or x equals 0, or x plus 1 equals 0, or x minus 1 equals 0, so really I have 0, 0, negative 1, and positive 1 as my zeros, or my solutions. But the 0 repeats itself. And that happens when your factor has a power that's higher than 1. If you've got a repeated factor. And when you have a repeated factor and it's repeated by an even power, then it's going to touch the graph like this one does. And if it's repeated by an odd power, it's going to cross the graph. I'm going to show you an example on Desmos. If you look here at this particular graph, I just made it up, but the polynomial. This has the factors x plus 2 squared times x minus 1 times x plus 1. So there are actually 4 factors here. There's an x plus 2 times an x plus 2 times an x minus 1 times an x plus 1. But this x plus 2 repeats itself, right, because it's squared. So I could set each one of them equal to 0 to get x equals negative 2. And you can see over here on the graph that it crosses it, or it touches at x equals negative 2. And then it also crosses at x equals positive 1, and it crosses it, or excuse me, negative 1 and x equals positive 1. It crosses at all those places because those are the zeros of this function. If these are the factors, then, excuse me, if these are, the factors, then the zeros are negative 2, positive 1, and negative 1. But negative 2 repeats itself because 2 here, this 2 that I'm circling with the arrow or the cursor, it's even. That means that this is going to come down and touch the graph and then pop right back up. That's going to be a local extrema. And then it's going to cross again at those other zeros. That's if your repeated power is even. I'm not talking about the power of the polynomial. I'm talking about the power of the repeat. Now, if my power is odd, it's going to cross at that repeated point instead of touching. So I'm going to erase the red one and I'm going to put on the purple one here. So I've got x minus 2 to the third times x plus 1. And if I were to set each one of these equal to 0, I would get x equals 2, x equals 0, and x equals negative 1, which you can see at it crosses at 2, 0, and negative 1. But here, this is repeated, so it's really x is 2, x is 2, x is 2, x is 0, and x is negative 1. But because this power, the repeated power is odd, the graph itself doesn't touch, it crosses at that power, or at that 0, or at that x value. So on the red one, because this is an even number, it would touch at that a, but the purple one is odd. The power of the repeat is odd, so it crosses at that a. So it does have 5 local extrema, or excuse me, 5 solutions, but 3 of them are the same solution. Therefore, there's 3 repeats and 2, so it has 5 real answers, but 3 of them are repeats. So it looks like it just has 3 answers. And so you would really only say that it has 3 zeros, because it really only touches it in 3 different places. Okay, does that make sense? This is on page 104 of your book. There's an example of how to, or not example, if there's a blue box that explains this. But I thought it would be easier to see on the on Desmos. This video is getting very long, and a lot of the examples that are left are just further examples of what we've already done. So I am going to have you read some of them, but we're going to do one more together, and then I'm going to have you read the other ones and study them on your own. I want to look at example 6 on the bottom of page 104, and we're going to do 6a. Now it says find the polynomial functions with the following zeros. There are many correct solutions. If negative 1/2 is a zero of a particular polynomial function, then isn't x minus 1/2 minus negative 1/2, a factor. So I'm going to rewrite this as a factor, x minus negative 1/2. And if 3 is a 0, then x minus 3 will be a factor. And if, again, repeated, like we had before, x minus 3 is a factor. Now this is simplified x plus 1/2 times x minus 3 squared. And that's going to be equal to my f of x. Now I don't really want to deal with a fraction here, so I can rewrite this. If I take both of these terms and I multiply them by a factor of 2, I can get rid of my my fraction, can't I? In other words, if I take, this is just scratch work over here, 2 times x plus 1/2. 2 times x is 2x. The 1/2 cancels it out, and I'm left with 2x plus 1. This is really the same factor as that, because if I set my 2x plus 1 equal to 0 over here and solve for x, 2x would equal negative 1, and x would equal negative 1/2. So it solves down to be the same thing, right? So I think I'd rather write it without a fraction. So I'm going to write this as f of x equals 2x plus 1 as one of my factors, and then x minus 3 squared as my other two factors. Now, I need to go ahead and simplify this out. So x minus 3 squared is, when you multiply two binomials together, you square a binomial, you're going to get x squared minus 6x plus 9, right? When I FOIL that out, or just multiply two binomials that are the same. And then I'm going to distribute my 2x plus 1 to everything. So when I do that, I'm going to get, my top one is going to be 2x to the third power, because I'm distributing 2x to all the terms right now first. Okay, so 2x to the third power minus 12x squared plus 18x. And now I'm going to distribute, let's see if I can change my pen here, the 1 to all the terms in here, right? So I'm going to be left with x squared, minus or plus a negative 6x plus 9. I'm getting to the bottom of the pad here, so it's harder to keep things straight. And when I add all these together, I end up with 2x to the third minus 11x squared plus 18 minus 6 is 12x plus 9. So f of x equals all of that. And that is how you take numbers that are zeros of a function and write what the function is, or write the polynomial from that. If you're given factors or if you're given zeros, you can find the function. Now, part B we're not going to do together. I'm going to let you study that one on your own. It's a little more complicated, but they do work it out for you. If you don't understand what they did, we will talk about it in class on Tuesday. Okay, but I would like for you to also study example 7. Why don't you read through that in the book and then try example 8 on your own without reading the solution, and then check it. And then I also want you to read page 107, the intermediate value theorem. I think it's easier for you to read it and then me try to explain it on here. And if you have an issue with it, we can talk about it again on Tuesday. So enjoy the rest of your weekend, and I hope this helps you with understanding section 2.2 of your book.